So without anything else to say, let me introduce Toby Cubitt from Phasecraft and UCL, and he's going to tell us something about quantum simulation and quantum-enhanced DFT.
Well, good morning. Thanks very much for being here so early. This might be the earliest conference talk I've ever given. I'm not a morning person, so hopefully I'm caffeinated enough to make sense. And thanks a lot to the organizers for inviting me. It's really nice to be here. I've never been to Rhode Island before, so I'm looking forward to seeing more of it. I got in late last night. I'm going to talk about some work that I did in Phasecraft. So I have two hats. I'm a professor at UCL. I'm also a co-founder of a spin-out company, Phasecraft. And this is work that was done within Phasecraft. And I should highlight the fact that most of the work was not done by me, of course. It was done by my collaborators and colleagues there. So Evan Sheridan, Lana, and Raoul. Raoul is also here at the conference this week, so feel free to go and talk to him about this. And there's an archive reference for most of what I'm going to talk about in the main part of this talk. So just a word about Phasecraft. We founded the company about nearly 5 years ago now. Myself, Ashley Montanaro, John Morton, and we have about a team of about 30 people now. Most of those are researchers, not 100%, but the vast majority are researchers based out of Bristol and London in the UK and also in DC in the US now. So let me warm up gently with something I think most of you in this audience are probably familiar with. But we founded Phasecraft to try and get useful quantum applications onto quantum hardware that actually exists now, not in 20 years' time, and useful in the sense of actually doing something that people ultimately would like to pay for. So if you think about the quantum algorithms we know, you kind of want to achieve three things simultaneously. So you ultimately want quantum computing, if it's going to be used for anything, needs to solve commercially useful problems. We want something that will work in the near term and not have to wait 2 decades or a decade or 2 decades for large-scale fault-tolerant quantum computers to come along where I can just program them assuming they're just an ideal computer and with as many qubits and gates as I want. We don't want to do that, wait that long. We want to do something in the near term and immediate term for it to be actually useful now. And we better beat classical algorithms, otherwise there's just no point building a quantum computer. It's much cheaper to build large classical computers. And if you just now spread the quantum algorithms that we know around this Venn diagram, I can argue a little bit about where these things should go, but it's unclear what exactly is in the middle here. And that's kind of the goal of in some sense, a large fraction of actual practical quantum computing and algorithms research is there a way of getting something into this intersection? So lots of people, it's not a novel thought that people have been saying for as long as I've been in the field, which is over 20 years now, that Hamiltonian simulation, simulating many-body physics, is one of the most compelling uses of quantum computers. And it's also potentially one of the ones that we might be able to do sooner than some of the others, like Shor's algorithm. But it's not clear whether you can actually do simulation on a near-term quantum computer that is actually beyond classical algorithms, is actually for a useful problem. No one has yet achieved this. So there are sort of two directions in simulation one could think about. I want to make a distinction between material science and chemistry. So if we look at materials, by that I mean periodic crystal lattices. We have a lot of useful things to work with. So we have translation invariance. We have point group symmetries of the crystal lattice that we can exploit. Electrons on a lattice site or in a unit cell only interact strongly with electrons nearby, not very, very far apart in the crystal. So roughly speaking, I'm a theorist, I wave my hands and say that roughly speaking, that means we can model these systems with short-range nearest neighbor interactions. And that means for each fermionic mode in the system, for each lattice site, we only have 0.1 Hamiltonian terms independent of the system size. Okay, I'm waving my hands a lot here. There's a lot of approximations I'm making and assumptions. But very roughly speaking, the scaling of the number of terms per qubit or per site is 0.1. If you look at chemistry, so by which I mean molecules, we have fewer symmetries, so there's less structure to exploit. And in a molecule, again, waving my hands a bit and making some kind of assumptions or rough approximations, electrons in any orbital in a molecule interact with electrons in any other orbital, which means we have all-to-all interactions in the Hamiltonian, which means we get n squared scaling of the number of terms per mode or per atom in the molecule or per electron mode or orbital. So if you look at this just on basic algorithmic grounds, we would expect that materials modeling is a little bit easier and less costly than molecular simulation. There's been a lot of focus on chemistry simulation in the quantum simulation community. And yet algorithmically we know that there's an order n squared scaling here that goes down to 0.1 for periodic materials. And that's important, given the limitations of current quantum hardware. We're like really limited with how much we can do, even though quantum computers can now do things that are not replicable on classical computers. They can't yet do something useful. We really care about n squared might be just big O of poly, but if you can get rid of an n squared factor in your algorithm, that matters a lot in terms of actually implementing it. The flip side is that for a periodic material, in principle, to simulate a whole thing, you're talking about like 10 to the 26 atoms. That's a lot more qubits than a molecule that might have a few hundred. So generally, rough rule of thumb, materials modeling, periodic materials, lower circuit depth than molecules, but more qubits. That's a trade-off. Given the current hardware, we're more limited by number of gates we can apply before the noise just swamps everything and you get garbage out than the number of qubits. And it's easier, not easy, but easier to scale the number of qubits than to improve gate fidelities. My contention is that materials modeling is a better early target for quantum simulation, and chemistry is going to take slightly larger, slightly more advanced quantum hardware. So what I'm going to talk about in this talk is mostly on this side. But we also look at chemistry simulation within Phasecraft, along with other problems that have nothing to do with simulation. But this talk, I'm going to focus on this side of this slide. So to take one example of the kind of thing we've done at Phasecraft, this is strontium vanadate is a transitional metal oxide that is an interesting material for next generation battery cathodes. So what we do in Phasecraft, we're not looking at like Hamiltonian simulation is a subroutine. It is not an actual application. You have to go, if you want to do something practical, you have to go take those quantum algorithms and actually apply them to something people really care about solving. So something real, a real molecule, a real material. So this is one example of a material that people are very interested in modeling in industry. Pre-Phasecraft, the circuit depth for doing a simulation of this was around 750 million gates. That's the circuit depth. So 750 million per layer. Post-Phasecraft, so about 4 or 5 years of research, we got that circuit depth down to about 880 per layer for this material. And what does per layer mean? Here, for any quantum algorithm to doing some kind of simulation of a quantum simulation task, whether that's trotterized time dynamics or variational quantum eigensolver with the Hamiltonian variational ansatz, essentially you need to implement a layer of the Hamiltonian and then repeat it. So this is the cost, the depth per layer, and then you have to do a number of these layers. And that's true whether you're trying to find ground states via VQE or whether you're trying to do trotterized time dynamics. How many layers and how you use the layers is slightly different, but the core element of the algorithm is the same. So let me give you, human minds are pretty bad at comprehending large orders of magnitude. So I just want to give you an idea of just how big a difference this makes in terms of the cost of these algorithms. So if I look at the best previous algorithm before we did our work in Phasecraft on this, and I'm going to zoom back to where we are now. And this gives you a sense of just how big a million-fold improvement in an algorithm actually is. Takes quite a while to get there. So we really hammered away at this to get the circuit depth down. Still going. That's how long you have to sit and wait to see the level of what a million-fold improvement in an algorithm's complexity or algorithm's cost looks like. So it's a big improvement. And how do we achieve this? We put together there's not one idea here. So this million-fold improvement in the cost of simulating this is an example that we can apply it to, doesn't come from like a single big idea. It comes from finding a factor of 2 here, a factor of 5 there. Okay, that's one order of magnitude. A factor of 3, another factor of 3. There's another order of magnitude. And just hammering away at this, doing, in some sense, what is more, it feels a little bit more like engineering than the kind of theory research I do in my academic life and still do there, where we're proving long theorems and making sort of huge, big O scaling improvements asymptotically. Here it's really like figure out every way of trying to squeeze something down And there's like 5 different clever ideas from designing better fermion encodings that are more efficient, that make the circuits slightly less costly, to all kinds of other things that come from optimizing on the kind of physics and chemistry level, to simplifying things down. And this is all described in a long Nature Communications paper that was on the archive a good couple of years ago, but published more recently, earlier this year. And we don't have people in Phasecraft who just do this with pen and paper. All of the ideas we had for how to optimize simulation of materials models are coded up into a whole pipeline where we can put in a description of a material in one end. It applies all of the clever stuff we came up with and optimizes it for that particular material and spits out a quantum circuit that if only we had a big enough quantum computer, we could run. And so I gave you the example of strontium vanadate, but we can run any materials through this pipeline. And indeed, if you go to this URL, you will find we've run about nearly 50 different materials through this pipeline. And you'll see figures there for how the comparison between what you could do previously and the circuit depth cost that we have got things down to now. So you can go on there and just have a look up your favorite material. There's examples of lots of different types of materials, ranging from simple things like silicon or salt through to complex transitional metal oxides. However, that sounds great, but 880 per layer, to do something useful with that, you need to multiply that 880 by the number of layers you need to do. So if you're very optimistic, maybe in VQE, you need 3 layers if you're super optimistic about VQE to get a good approximation of the ground state. For time dynamic simulation, you better do something in the order of hundreds of layers for a meaningful simulation of the time dynamics of such a system. Current quantum computers, the circuit depth you can run out to before everything falls over is maybe optimistically order of like depth 1,000. That's pretty optimistic. It's hard to get it to work at that depth on real hardware. But even on the world's best quantum hardware, if you take 3 times 880, if you're up to the mental arithmetic this early in the morning, that's bigger than 1,000 by quite a margin still. So 1 million-fold improvement in the efficiency of an algorithm, which is kind of unheard of in classical computing these days, is still not enough to actually simulate a useful material on a real quantum computer currently. And it's still quite a long way off. So this is pretty depressing. So 1 million-fold improvement in the cost of an algorithm is still not good enough to actually do meaningful quantum simulation yet. And that factor of roughly 3 in depth you have to go out to, that's still a big leap. Okay, that's because unless you do fault tolerance and error correction, you're losing exponentially in depth. The noise will accumulate exponentially. Your state will converge exponentially fast to the uniform distribution on the output. So that's kind of like you have to make exponential improvements in the gate fidelities to be able to push this out by another factor of 3. So given the immense complexity of trying to simulate even not a simple material, but strontium vanadate is a nice example because it happens to have a very simple band structure, which makes a lot of the costs. It's not the simplest material I could give you, but it's kind of the simplest of the interesting ones. Given the immense complexity even of simulating something like that we can't do it yet on quantum hardware, how is it that classical computational chemists and material scientists have been doing computational chemistry and materials modeling for the best part of 3 decades now, and getting really good results? So for that, I want to give you a brief crash course in density functional theory, which is the technique that essentially, especially outside of academia, in industry, people doing chemistry, computational chemistry or materials modeling, drug discovery, this is what they use. This is the algorithm they use to try and compute properties of molecules, materials, chemistry, computational chemistry. Almost all of it is done by a DFT. So I'm a born-again chemist. Those of you who know me from other talks, not with my Phasecraft hat on, I'm putting up theorems with 30-page proofs and a lot of maths. But in Phasecraft, I've become a born-again chemist, and this is DFT is amazing. And those of you who know it already know that. And so apologies to everyone who knows DFT very well, because I'm going to probably do a very cartoon explanation of it. But I think for some of this audience, those coming from the quantum information side of the community, maybe this is not so familiar. So let me give you a kind of brief overview of what density functional theory is. So here's the Hamiltonian of everything in the universe. At least everything in almost everything. So if I ignore nuclear processes, then everything is just Coulomb interaction between charged particles up to nuclear stuff, and we're not interested in doing nuclear research in Phasecraft. And okay, what I've written down here, it's Born-Oppenheimer approximation, so I've frozen out the nuclei, and this is just the electron part. But roughly, this is all of chemistry, all of material science, almost all of physics in one equation. And if we can solve this, if we were able to simulate or solve or derive properties of this Hamiltonian, then to a very large extent, with the exception of nuclear processes, and with some caveats around, I've made some approximations, but I could lift the Born-Oppenheimer approximation and put some more terms in here that look somewhat similar with different masses. We'll be able to essentially model everything, almost everything we're interested in. The problem is, of course, that this is extremely difficult to solve this Hamiltonian. So this is the electronic structure problem. When I've thrown away the nuclei, taken Born-Oppenheimer approximation, just written down the electron part of my Hamiltonian. So density functional theory is founded on a sort of collection of two collections of theorems. The first are the Holmberg-Kohn theorems, or there are sort of generally stated as two. So first, let me introduce. So this is not the density matrix. This is the density in the ground state. So take the ground state of this Hamiltonian, and now look at the expectation value of the number operator. So these are fermionic creation annihilation operators. C dagger C is the number operator at position R, and then the density, I should have put an R here. This is a function of position. This is the expectation value of the number operator as a function of position in the ground state. So that's the ground state density. Don't think this is not a density matrix. I'm sorry, they use the same letter, rho, for that as we do in quantum information and quantum mechanics for the density matrix. The first Holmberg-Kohn theorem says, and note that this is not unique. So for any density, there are multiple different wave functions that would have the same density function. But the first Holmberg-Kohn theorem says that for this Hamiltonian, there's a one-to-one correspondence between the ground state density and the ground state wave function. I.e., if you've got the ground state density, there's a unique wave function that can be the ground state of this Hamiltonian that has that density. It's not a difficult proof. It's in fact, go read it. It's an elegant sort of three-line proof. And the second Holmberg-Kohn theorem says that if you minimize, you can write the energy as a functional of the density. So the density is a distribution of electron density in space. So that's a function. If you have a functional, so a function from a function to the reals, you can write down an energy functional that's just a function of the density, not the ground state wave function itself. And the ground state density is obtained by minimizing this functional over all possible densities. And there's some things one should take care of this being kind of representable as n representable as a density that comes from a wave function that satisfies the fermionic symmetry. But I'm sweeping some stuff under the carpet here. So these are the two Holmberg-Kohn theorems. Again, not a difficult proof. It's almost kind of very straightforward to derive that just from the form of this Hamiltonian, but very deep. And I can write this energy functional as a kinetic energy part and something that isn't in the literature usually called V stuff, but this is just like I'm stuffing a whole load of stuff into this, which you can expand out. So some parts of this are coming from this is the position of we've got an atomic potential, so our nuclei are at certain fixed positions, and so then that creates a fixed background field for the electrons to move in, so that gets shoved into here. A part of the Coulomb interaction, you can take part of that and put it into this term. And then there's some leftover stuff, usually called the electron correlation, or the VXE, the exchange part of the exchange correlation part of the functional. And why this separation? Because a whole bunch of parts of this functional are actually classically efficiently computable. So all of this, the contribution to the energy as a function of the density, from this part, there's a classical polytime algorithm for computing this. Okay, it scales with the number of fermionic modes, not with the dimension of the Hilbert space. So it's like, translated to qubits, it scales with the number of qubits, not 2 to the n, not the Hilbert space dimension, to compute this. And then there's this part. And this part, note, depends, if you look back where it comes from, this just comes from the Coulomb interaction. So it's just coming from the electron-electron interaction. It doesn't have anything to do with the position of the atoms in my crystal lattice or in my molecule, so this is completely universal. No matter what material or molecule we're trying to model or simulate, this term, we're computing the same thing, the same functional for this. So this is called the universal functional, or some part of this. So we just need to do this. It's just part of the contribution from the Coulomb interaction between electrons. So the second part, the pillar of density functional theory, is, or at least the most popular form of density functional theory, the Kohn-Sham theorem. So Kohn and Sham won a Nobel Prize for this. And the Kohn-Sham theorem says that this turns this into a practical, this insight of the Holmberg-Kohn theorem into something practical, into an algorithm that you can actually use to try and use this approach to actually solve electronic structure problems. So what the Kohn-Sham theorem says is that for any ground state density, there is some potential, so some term in Hamiltonian, some interaction of this form, or some Hamiltonian term of this form, such that the ground state density, so the ground state density is given by minimizing a new functional, the kinetic energy part plus this Kohn-Sham part, by minimizing this over all densities. But the important thing is that this term here, so this is the kinetic energy contribution just from non-interacting electrons, and this is a potential that doesn't involve electron interaction. So if you're not familiar with fermions, if you are, you'll know that any fermion-fermion interaction, you have to have 4 creation annihilation operators. It has to be degree 4 in the creation annihilation operators. This is degree 2. This is not an interaction. This is just a single particle potential. So this is a single body problem. This is just a problem for non-interacting electrons, and this can be solved efficiently on a classical computer. So Kohn-Sham theorem says that we can replace this functional by a new functional that's really easy to solve, and we will get the same answer out. So this gives rise to the Kohn-Sham DFT algorithm, or procedure. And we start off with some guess at the density, the ground state electron density. From that density, we can derive this fictitious Kohn-Sham potential. And then once we have that, we can find the ground state density of this fictitious system, and get an updated guess, or an updated description of the density. So the thing is that the Kohn-Sham, this fictitious potential itself, depends on the density. So we have to solve these equations iteratively. So we can iterate these self-consistently until convergence, and you can show that this will give you the ground state density. If only we could compute this thing. But of course, there's no free lunch. Okay, so all Kohn-Sham did in their Nobel Prize-winning work is to shove all of the difficulty into some new thing that they defined and capture all the difficulty there. But it hasn't changed anything, right? There's no free lunch for making this problem easy. I mean, we know as quantum complexity theorists, this problem is QMA hard, so we don't even expect to be able to solve it for every system on a quantum computer, let alone a classical one. So obviously, this step now is the hard step. Computing, and indeed the only part that's difficult in order to compute this fictitious Kohn-Sham term, what we need to do is to compute, the only difficult part is the part this universal part, that's this exchange correlation part that isn't efficiently classically computable. So if only we could compute this exchange correlation contribution, we would be done, and we'd have an efficient classical algorithm for solving every problem in the universe, modulo nuclear physics. So unfortunately, of course, we've just hidden all of the complexity in the difficulty of computing this functional. So this must somehow capture the entire difficulty of ground state, electronic structure ground state problems. This must be at least QMA hard to compute in the worst case. So what do classical computational chemists and materials modeling people do in practice? And this is why the Kohn-Sham and density functional theory is a very useful, practical, and very effective algorithm, is that you replace this universal thing that we cannot compute, and provably, complexity theoretically can't compute efficiently in general, with a good approximation to it that can be computed efficiently. So for example, one of the original approximations is to take something called the local density approximation, which you just take a functional form that comes from looking at the non-interacting electron gas, and you take that as the form of your functional and replace VXE by this thing that's easy to compute. And why is this Kohn-Sham DFT such a win? It's because you've essentially computed everything you can compute efficiently classically. You've computed efficiently classically and accurately. And what's left over is a small contribution that is difficult to get accurately, but is generally a small contribution to this. So making an approximation just to this difficult to compute part, where you've pared down the difficult thing to just the thing that you can't compute and done everything else, computed it essentially perfectly. You could often get good results from doing this, even though you're using an approximation to this universal part. So this is why Kohn-Sham won the Nobel Prize for this work, is because this actually works in practice, gives very good results. Okay, but unfortunately it doesn't always give good results. So DFT, there are some problems where density functional theory, it simply solves the problem. You don't need a quantum computer. There's no point being a quantum computing theorist or even a quantum computing entrepreneur. Classical computers already solve the problem, and you just don't need quantum computers to solve this. But those are problems where the exchange correlation contribution, hand-wavingly correlations between electrons, or in kind of quantum information language, entanglement, except I want to be a bit careful about talking about entanglement between fermions. Where that plays a significant role in the physics, density functional theory goes badly wrong. When these approximations are not good, like approximating, for example, just by something coming from modeling non-interacting electrons, when the electron-electron interactions play a significant role in the physics or chemistry of the system, then this goes badly wrong, and DFT gives you very poor results. Sometimes you take a material, you run it through DFT, and it will predict that it's an insulator, and you go to the lab and measure it, and it conducts. That level of wrong sometimes. Even something simple like silicon, where DFT works pretty well, the band gap of silicon still cannot be computed numerically correctly by DFT. It gets it qualitatively correct, but the band gap of silicon, still the true band gap that you can measure in the lab, is still not predicted by DFT. And silicon is a pretty simple material. Okay, so I want to spend the remainder of the talk talking about a new algorithm that we developed in Phasecraft that is a quantum-enhanced version of DFT. So having presented like this, I think this idea in some sense is really quite obvious, and then you've got to make it work. But since the only difficult part in DFT is computing this thing, this is a many-body Hamiltonian. It's electron-electron interactions. Quantum computers ought to be very good at solving quantum many-body physics problems. So why don't we use a quantum computer to compute the exchange correlation part and use that in DFT instead of one of these classically efficiently computable approximations? So just compute this on a quantum computer instead of a classical computer. So what do we need to compute? We just need to we want to compute the ground state energy contribution subject to the ground state having the I clearly was asleep when I wrote these slides, because this shouldn't be mod psi squared. This should be the ground state density, so the expectation value of the number operator should match up with whatever the density is we're trying to evaluate this contribution at. Okay, so minimize subject to a constraint on the wave function. And this isn't something that we expect to be easy for all systems on a quantum computer. It's QMA hard, but that doesn't mean it can't do better than DFT, where it's QMA hard. We get pretty good results by doing approximations that definitely throw away some of the physics. Here we ought to be able to do better by throwing away less of the physics and trying to compute it on a quantum computer. And you just need to compute this by your favorite ground state algorithm. So VQE or DQE, which I like better because I invented it, or your favorite quantum ground state algorithm. There are lots of other ones out there, like Quite, Pite, whatever your favorite is, you can throw it at this and use it to enhance the DFT by doing hopefully better than the classical approximations. I should caution that you're up against 40 years of very smart people doing research on how to do much better than the LDA approximation here. So this is a very poor, people do not use this these days. There's much better functionals here. So you're up against people who've been solving this problem in reality for real materials in a context where they really need the answer in industry with lots of budget behind it and huge HPC for 40 years. Nonetheless, quantum computers are incredibly powerful. 50 qubits for sufficient circuit depth we cannot simulate on a classical computer. So we're already at the stage where we can do things beyond classical, just not useful things yet. So there's hope. Okay, so let me dive a little bit more into detail about how this works. I'm going to do it in the context of a simple toy model, which is a very useful benchmark for trying to do electronic structure problems on a quantum computer. So the Fermi-Hubbard model, which is really just a very, very pared down, simplified model of the toy model of the electronic structure problem. But it's a useful one because it's a good stepping stone. If you can solve the Fermi-Hubbard model on a lattice, it's a good stepping stone to real-world materials problems and even chemistry problems. So this Hamiltonian, it's a fermionic Hamiltonian. It has a contribution that's just the hopping term, so electrons can hop between neighboring lattice sites. You have an on-site interaction between spin up, spin down. Each site has two electron modes, spin up and spin down, and there's an on-site interaction when there are two electrons in different spin states in the same site. And then you might have some external field that is, at each site you have a different external field. I think of this as a model of like the potential coming from the nuclei in a molecule or a material. So on a lattice, I've now put everything on a lattice, right? Not everything I described before. I was describing density functional theory in the usual way, where we're talking about wave functions and densities in real space, in 3D space. Here we're on a lattice, so now the density is just, okay, this shouldn't say functional, this should say function. The density function is just a list of the local operation numbers, so the expectation value of the number operated at each site in our lattice. So now it's just a vector, it's not a function. So I've discretized space. And now if we follow the Kohn-Sham procedure, but now on the lattice, so I can split up the contribution to the, remember the Holmberg-Kohn theorem tells us that the ground state energy is just a function of the density, so we can just work with this thing, not the wave function. And the theorems, which are really theorems, they have rigorous proofs, tell us that we're not going to miss it. This is going to give us the correct answers if we can make this procedure work. We've got the kinetic energy contribution, we've got the Hartree contribution is something, it's easy to compute this, so therefore we compute it classically. And then you've got the exchange correlation energy, the contribution from the external potential. And now let me actually define what this exchange correlation term is. It is literally defined as just everything, the whole energy minus all the bits you can compute. It's literally just that. Okay, so it's literally just jump everything you can't compute by definition into take the total energy and then just subtract off everything you can compute easily. That's the definition of it. So on the lattice, this is just, and here I've written it correctly, so find the ground state subject to the density being the one matching up with the one you're trying to evaluate this functional at, minus the stuff you can compute easily classically. So the ground state energy is given by the, remember our Holmberg-Kohn theorems? Our ground state energy, and from that the density, is just given by minimizing this functional overall. These are now just vectors. If I've got n electrons, or n electron fermion modes, this is a length n vector, not 2 to the n. Now if I take the derivative of this, with respect to the density or the occupation at a given site, I end up with this equation, and I want to minimize. So I want to minimize this. So I want the derivative to be 0, with respect to the density. So I just take the partial derivative with respect to each component of the density vector. I just get and set it equal to 0. I get this equation. So it's just elementary high school calculus. But this is, if you look at this equation, this is just equivalent to solving a fictitious non-interacting Kohn-Sham problem. So this is going through the Kohn-Sham procedure, but on a lattice where it's perhaps a little bit simpler to write everything down. Because this is just the same thing as we get the same solution if we solve the non-interacting problem for potential kinetic energy term plus just an on-site potential, where our potential is defined to be the one coming from all of these bits. So the external potential, the Hartree term, and the exchange correlation term, which are given by these derivatives of these energy contributions. Okay, so this is the Kohn-Sham approach done on a lattice. So we've reduced this problem to now, and this is a non-interacting Hamiltonian. Okay, so this is easy to solve classically. Okay, the problem is just computing this fictitious Kohn-Sham potential. So we just need to do this, and because this manifestly this depends on the density itself, so it depends on the n sub I, the expectation value of the number operator at each site. We, as I outlined before, but now doing it all on the lattice and a little bit more precisely, I just need to start with some guess for the ground state density or the on-site occupation number at each site on my Fermi-Hubbard model. From this, I need to compute the potential, the Kohn-Sham, fictitious Kohn-Sham potential. Then I solve this non-interacting fermionic Hamiltonian, which is easy to do classically. It's a polytime classical algorithm to solve non-interacting fermionic problems. And then I get an updated values for my ground state occupation numbers or ground state density vector. And then I iterate, and I solve this, I iterate this to convergence. So I need to compute now this Kohn-Sham potential from the density vector. So, okay, what do I need to compute? The external potential is just given as input to my problem, so that's easy to compute. The Hartree contribution is something that is classically efficiently computable, so that I can just compute on a classical computer. The only thing I need to do is to evaluate this thing, this exchange correlation part. So for this, what do we need to do? Well, this, I wrote down the energy contribution exchange correlation part before. It's literally just the ground state energy subject to a constraint minus all of the stuff that's easy to compute classically. I just need to compute this thing. This is by definition classically computable efficiently. We subtract it off, and we just need to take this correction, this quantum correction is the part we need to compute, and it's hard to compute. And this we can evaluate. One option is to evaluate this directly on a quantum computer using constrained VQE. And that's something we call online QEDFT in the paper. Or it's a version of online QEDFT, because this means that every time in your DFT loop you need to evaluate this thing, you call out to your quantum computer, run a constrained VQE optimization, for example, or your favorite ground state algorithm to compute this contribution. But for Fermi-Hubbard models, so there is a simplification we can make for something like the Fermi-Hubbard model that makes this actually a bit easier. And I think I have time to talk about this. And this is inspired by classical density functional theory. We can use the local density approximation to make this problem for the quantum computer a bit easier. And this works well in practice for lattice models like Fermi-Hubbard model. So we can address it like this, but we can actually simplify a bit, at least for something like the Fermi-Hubbard model, and make it work in practice and make this a bit of an easier problem for the quantum computer to solve. So remember this exchange correlation contribution, this is universal. This just captures the electron-electron interactions. It's independent. You have to compute the same thing regardless of what there's no contribution here from the on-site potential that's the problem-dependent part of this. It's just electrons interacting with electrons. So at least in the thermodynamic limit, this is translation invariant. The ground state should therefore be translation invariant. The density in the thermodynamic limit of the homogeneous case, so there's no on-site potential here. There's no external potential. This is just the Hubbard model, homogeneous Hubbard model. So the ground state should have uniform density by symmetry, which means that the ground state energy, the exchange correlation contribution, and hence the VXE contribution to the Kohn-Sham that we need to compute, the derivative of this basically that we need for the Kohn to compute this Kohn-Sham potential, is just dependent on if the density is uniform, then the density at each site, the expectation value of the number operator divided by the number of sites, is the same at each site in the ground state. So we should be able to reduce this to a function of just a single parameter, which is x, which is the local density, which ranges between 0 and 2. So you can have 0 electrons at a site. You can have 2 because there are 2 the spin up and spin down. And of course, the expectation value can be anything in between there because we can have superpositions. So this applies a simplified approach to QED, applying this quantum-enhanced DFT to at least to this particular case. We can evaluate this energy on the quantum computer at each point x. So if we've got a finite lattice, we find the ground state of the Fermi-Hubbard model on that lattice for all the possible different numbers of electrons that we can fill it with, a number of fermions. Okay, so that means the number of electrons, or maybe I should have written number of fermions, can range on if I've got a lattice of a certain size, then I can fill this system, this fermionic system, with between 0 and 2, because of the spin degree of freedom, times the number of lattice sites. And this gives me a discrete set of x's I can evaluate this functional at on my quantum computer, depending on how large a Fermi-Hubbard model how large a lattice I can fit on my quantum computer, or I choose to fit on it. So now we've evaluated this functional, although this functional is now a function of a single real number. So it's really a function now. And I just get a set of points, and I can interpolate these to obtain a smooth curve and obtain a function that's now I can evaluate this exchange correlation contribution at any local density. And then I take the derivative to find Vxe, as we saw on a few slides ago, and then I use this resulting continuous functional in the DFT loop. But now I've computed all this up front. Right? This doesn't depend on the problem I'm trying to solve. It doesn't depend on the external potential. So I can compute all of this up front on a quantum computer and then just save the results and derive this function. And I can just store that, and now I can use that function in my DFT loop without needing the quantum computer again. So this approach lets us do something. It simplifies what the quantum computer has to do a bit. We can do the computation up front. It's a somewhat simpler computation. We're not doing constrained ground state optimization. We're just finding the ground state at different filling numbers. And then we've pre-computed that all offline, and now we can use that function we've derived. It's now just a classical thing we store. And now we can use that to solve any problem for any external potential. There are two important advantages. Well, there's one big benefit of this that I may have passed you by as I'm going through this relatively quickly. So note that what happens if we manage to fit a bigger lattice on the quantum computer and solve the ground state problem on the homogeneous Fermi-Hubbard model at a larger lattice size? It just means we get to interpolate this function at more points. So we get a finer-grained, discretized evaluation of this function. So the larger the quantum computer, i.e. the more qubits we can fit and the better our VQE algorithm, as long as our VQE algorithm or ground state algorithm continues to work, the more precise a functional we get. But the size of the quantum computer does not constrain the size of the system we can solve with the quantum-enhanced DFT. It just changes the accuracy to which we can evaluate this functional. So once we've interpolated a continuous functional, we can use this functional at any point x, which means we can use it in a DFT loop for any lattice size and any external potential. Okay, so this means that the problem we're trying to solve doesn't have to fit in our quantum computer anymore. The size of the quantum computer and the quantum computation we can do just determines how accurate our approximation to the functional is. So I'm nearly out of time. This is the first point advantage, but the other big benefit is the quantum computer isn't being used to compute the output. We're not getting our output from the quantum computer. We're just using the quantum computer to steer a classical algorithm to a better fixed point, an iterative classical algorithm. And that means that even noisy quantum computing with relatively low output fidelity can potentially give accurate final outputs, because the final output is coming from the classical computer. The quantum computer is just steering the classical algorithm to the right solution. So I really do only have 2 slides left. Here are some results. So these are numerical. These are results done on classical numerics, not running on an actual quantum computer. And the key thing here is this is for the Fermi-Hubbard model in a Gaussian potential. 1D Fermi-Hubbard model because then we can essentially solve things exactly for 1D and compare to the exact solutions. And the exact solution is the red curve. The classical DFT is this blue curve, and you can see it completely misses these these shoulders here that are to do with the Mott phase in this system. Whereas QEDFT, with using VQE to depth 2 here, that orange curve and the red curves are almost over the top. So we can see that in this 1D Fermi-Hubbard model, this is on 200 sites, half filling. QEDFT is getting the physics right, whereas the conventional classical DFT is not seeing the right physics. But we went further than this and actually ran this on Google's quantum hardware. And again, short story is same thing. On real quantum hardware, where now we're actually got real noise and noisy output from the quantum computer and gate fidelities that are not perfect. Again, we see that the QEDFT run on a real quantum computer is capturing the Mott phase, whereas the conventional DFT is not. Okay, and we've also run this on 2D systems and other things. This is not yet quantum advantage, because the quantum computation we're running is small enough to mean you could just brute force simulate that classically. But this gives us a very promising stepping stone to actually, if we can run this on a slightly larger quantum computer where we can go beyond anything that can be just classically brute force simulated or computed via clever tensor network contraction techniques. This gives us a pathway to using small, noisy quantum computers to actually solve big problems. So with that, I'm done. I think my main conclusion is this quote that was actually in a report to the US Senate a few years back on classical computing. But in this report, it has this very nice phrase, which I really like to repeat in the context of quantum computing, which is that theory beats Moore's law by multiple orders of magnitude. Quantum computers are getting better. The hardware is getting better. If you track it, actually roughly exponential improvements, but it's with a low constant in the exponent over the years. Whereas these kind of theory improvements can bring down the cost of actually implementing something useful on a quantum computer much, much faster than the hardware can progress. So if you like doing this kind of theory and want to apply it to real-world problems, we're always hiring at Phasecraft. Come talk to me or to talk to Raoul in the audience if you want to hear more details about this piece of work. I put the archive number at the beginning, and thanks a lot for listening.
Thank you very much. Unfortunately, we only have time for 1 or 2 questions, so please.
On the results that you just showed, so you had 3 different things labeled DFT, DFT, ED, HF, and BALDA. What's the difference between those? Are they different functionals?
So the results I put up are for 1D. BALDA DFT is essentially giving the exact solution. It only works because the 1D Fermi-Hubbard model can be mapped to the Heisenberg model, and then you can use it's exactly solvable essentially. So the DFT BALDA here, this is why we're doing the results I showed are in 1D just so we can compare to exact results. On 2D, I don't have an exact result to compare to. So the DFT BALDA is giving the exact results. DFT HF is the Hartree-Fock DFT. So it's kind of standard conventional DFT approaches. DFT ED is cheating and just we're on a small enough system here that we can just do ED to find the ground state. So it's another way of looking at what the exact solution is. And then the QEDFT is doing different simulations of VQE at different VQE depths, and then this one is the hardware one. In the paper, you'll see more results on other systems that are not just 1D, and but it's nice to do 1D where you can compare with the exact solution to see how well you're doing. I should emphasize that for Fermi-Hubbard models, DFT is not the best classical algorithm, okay? So the best results for Fermi-Hubbard are using quantum Monte Carlo, and they can go out to 20 by 20 lattices, or 10 by 10 at least, and get good results. But quantum Monte Carlo does not perform very well on real-world problems. So this is comparing sort of with the technique that you would want to use on something like strontium vanadate, but on a system where DFT is known that it doesn't perform super well. So it's just indicative. This is not yet quantum advantage, but it's a pathway.
Just quickly, by Hartree-Fock DFT, do you mean just Hartree-Fock with Hartree-Fock exchange and no correlation?
I suggest go talk to Raoul in detail and read the paper. Roughly yes, but I want to leave time for one more question.
All right. One other question.
Right here. A microphone for you, sir. So we know that in the 2D Fermi-Hubbard models, there are many competing phases with ridiculously small energy differences between them. Frankly,
Yes.
it's hard to believe that DFT-type approach can capture this.
I'm not sure. I don't particularly want to use DFT to solve Fermi-Hubbard models, at least in Phasecraft, because I don't think anyone will pay me to do it. I really care about using DFT to solve molecular systems or materials. Hubbard it's a useful test bed for two reasons, I think, for quantum algorithms, simulation algorithms. One is it's a fermion system. Okay, its spin models are much easier to do, but you don't have to pay the cost of getting fermions onto mapping fermions to qubits, and that matters. And if you duck that problem by solving spin models, you've still got that challenge to go when you want to try and go to real-world problems, because the real-world problems people care about simulating are essentially all electrons. That's one reason why I think Fermi-Hubbard is a better test bed than spin models. And the other thing is it's known to be difficult, classically. There are lots of models where they're very clever, or you can invent some new model, and then maybe just some smart person will come along the next day and find a clever classical way of getting better results than the quantum computer can. That's happened many times in the history of quantum algorithms and quantum simulation. So you don't want to kind of make up a new problem. I like test bed problems where we know that it's difficult because very smart people for like best part of half a century have been attacking this. But it's just a test bed. So I don't expect just the DFT approach to necessarily capture the phase diagram of the Fermi-Hubbard model. But it's a good test bed for early stage quantum computers before jumping to real world problems like transition metal oxides or molecular systems. I don't know if that answers your question, but that's my... No. Let's talk.
Like a comment. Somehow something's wrong with your Hartree fork because it doesn't show a plateau at half filling. I think you did not introduce enough symmetry breaking states.
Okay, this is a good point. So you can tune up DFT to do much better than this for a particular system and use hybrid functionals, and you can get better results than this, yes. But I don't want to compare with that because that's not the quantum algorithm doesn't use any kind of tweaking or hyperparameters for any particular system. It's just a black box. So I want to compare with the black box approach here, not to I can tweak functionals even on real world problems. I can use hybrid functionals that I tune up with various hyperparameters and match up with experimental data and get much better results. But that's a pain in industry. That's really, in real world people would, in industry, not in academic research, people want to have something that you don't have to tune up a whole bunch of hyperparameters. So yes, I can do better than this with DFT, but I want to compare with an approach that's like for like.
All right, let's thank Toby again.